Imagine we ask a large model a question. Which animal is best known for pulling sleds through snow? It chooses husky. We want a much smaller model, one we hope to run on a phone, to answer the question too without asking the large model every time. Copying the teacher's parameters sounds reasonable, but the student has fewer parameters, so the teacher's full set does not fit its design. So we use the teacher during training. For each example, the teacher produces a prediction, and the separate student learns to make its own prediction closer to it. This setup is called knowledge distillation. 4 connected pieces explain how the answer could eventually come from a model running on a phone. They are the student's smaller design, the teacher's training signal, the behavior the student keeps or loses, and the deployment work that follows. We begin with the student's design because its size is chosen before the teacher helps train it. Here is that choice in a real model. BERT-base has 12 stacked processing blocks called layers. For DistilBERT, the designers chose a student with 6 layers before distillation training began. That halves the layer count. Across the whole model, the number of parameters falls from 110 million to 66 million, a 40% reduction. Those 66 million are the learned numbers the later training can adjust. Distillation now works inside that boundary. Training uses teacher signals to adjust the student's 66 million parameter values while its 6-layer design stays fixed. With less room available, the next step is to see what information the teacher sends. Now we return to our sled question with its smaller student design already fixed. If we train it with only the hard label, the target marks husky at 100% and wolf, fox, and toaster at 0%. That target identifies the correct answer, but gives no information about how the other answers compare. The teacher gives us its full prediction over the same 4 answers. In this worked example, it assigns about 72.7% to husky, 26.8% to wolf, 0.5% to fox, and 0.003% to toaster. Husky still wins, yet the losing answers show that the teacher treats wolf as a much closer alternative than toaster. For training, we can turn a setting in the probability calculation called temperature up to 4. The teacher's underlying scores stay the same, while its prediction changes to about 46.6% husky, 36.3% wolf, 13.3% fox, and 3.8% toaster. The ranking stays the same, and the smaller answers become easier to compare. We call this spread out prediction a soft target. Temperature exposes the teacher's existing judgment more clearly without adding new knowledge. A soft target can carry useful distinctions, teacher mistakes, and biases into the student. Training turns targets like this into student behavior by using them across many questions. Take the first question from that waiting row. During training, the teacher attaches a soft target, then does the same for the other questions. Good, but so far all we have is a stack of targets. The student itself has not changed. Now let the student see one of those questions at the same training temperature. It makes its own distribution, and the 2 sets of bars do not line up. Training compares them answer by answer to find where the student's prediction disagrees with the target. Training uses the mismatch to adjust the student's parameters. The student's design stays fixed as this compare and adjust cycle repeats across many questions. Each update aims to bring the student's predictions closer to the teacher's targets. When training ends, the temperature returns to 1 and we close the training workspace. A new question goes only to the student, which answers using its learned parameters. The teacher, soft targets, and comparison step do not run at inference time. Training is finished, and the student can now run alone. But it still has to fit within the phone's limits. To see the storage problem at a realistic scale, take a model with exactly 3 billion weights. At 16 bits per weight, those weights alone take 6 gigabytes. At 2 bits per weight, they take 0.75 gigabytes. These figures count only the weights. Running the model requires additional memory for cached context and temporary calculations. Quantization creates this storage reduction by representing each learned weight with fewer bits. Distillation changes the training signal used to learn those weights. The two techniques help the same student in different ways. The student's smaller architecture reduces the work the phone must do. Quantization reduces the space needed for its weights, and the device runtime runs the model on the phone. With those pieces in place, the trained student can face the original sled question on its own. In our example, the student on the phone now answers husky to the original sled question. Only the student is running. The teacher finished its part during training, so this answer comes from the student's own learned numbers. Work backward one step. This student can run with less inference cost because engineers chose a smaller design before training. It has fewer learned values and operations to store and run. Its size was already fixed when the teacher guidance began. During training, the teacher supplied full predictions over many questions, including the relative probabilities. Training adjusted the student's own values to make its predictions closer. That richer guidance can make the chosen small model more capable. What survives is a selective approximation. The student sees the teacher only through those questions, and the student's capacity and training determine how much of that signal it can fit. Getting the trained student onto the phone requires separate work to reduce its storage and memory use and run it on the device. Knowledge distillation is offline training that uses a teacher's outputs to make a chosen small model more capable. Separate engineering makes that trained model phone ready.